Okay, hello everyone. Welcome back. It's been quite a while again. Uh, I am terrible with this. I'm still trying to set up a schedule for the uploads, but I have other things that I need to worry about. So today we will be talking about logistic regression, the next machine learning model, and this video is going to start off a bit differently. I will go over my notes about the model, and I will point out some of the interesting things about the methods and like about its nature. And then we will move on to the code implementation in the next part. And again, it's we're gonna just explore how I implemented it and how we trained it. So first off, I would like to say that logistic regression is quite similar to linear regression, with just a difference of usage of sigmoid function at the end of it to get the scaled down results. Yeah. So again, yeah, this is quite similar to linear regression. And another different thing about this is, even though its name suggests that it's used to predict numerical values, and we are going to do so, but essentially it is just a supervised probabilistic classifier. So this model is used as a classification. This model is used as a classifier in classification tasks, even though the name suggests that it's regression. So this is an important thing to know when talking about logistic regression. You need to know that it's a classification algorithm. Okay, and another thing that you need to know is we can use logistic regression to classify either two classes or multiple classes. And in today's example, we will go over two classes and the classification over these classes. It's titled binary classification problem. Okay, that's another thing to know. And let's move over to the another important point of the model. So as I stated earlier, this is quite similar to linear regression. The only difference is at the when getting the forward method, which was the multiplication of input and the weight matrix and bias added to it, we will also put these new results through the sigmoid function and get the end result of the output of get the end result from the output of the sigmoid function. So essentially, we will scale down the results that we're going to get in between 0 and 1. Okay, so in the middle of it, you can see the sigmoid function, and its expression is not hard to understand. It's quite simple in terms of like the expression. It looks quite interesting. So the first thing you need to know is, the larger you go in terms of the input, you will be much more closer to 1, but you will never reach 1, exact 1. Okay, but it will be pretty close, like maybe 0.999975. It will be pretty close. It's the same for negative big numbers. In that case, you will reach to you will get much more closer to 0, but not exactly 0. And the sigmoid function enables us to map real values to between 0 and 1. And there is a footnote here. This suggests that values near 0 and 1, as I said it earlier, which was pretty close to 0 and 1, these are considered outliers and these are flattened, which means that we are essentially getting rid of their effects on the model itself. It does not affect the model too much. And this function, the important part of this function is it is differentiable, which means we can calculate its gradient. This is important because, as you know, we use backpropagation when we are training the model, such as like we use stochastic gradient descent, right, as an optimizer. In order to use that method, we need to make sure that we can calculate the forward method and its gradient. This is important because we need to, you know what, I can actually open that note too. Was it here? No, let's not go over that. It will get complicated. But just that we need to be able to calculate a function's gradient or some sort of sequence of expressions gradient in order to use these optimizers. And this we can, like, if we add sigmoid to the expression, we can, like, nothing changes. We can still use these optimizers that capitalize on the gradient method. Okay. And sigmoid can be used to calculate probability. This is important for both classes. So at the end of this sigmoid function, what we get is we get a probability, which is just going to be a percentage. That's why they are mapped between 0 and 1. So you can think of these values as a percentage, or as a likelihood of a data point being a certain class. Okay. And we can actually see that here too in the middle expression. And there's another thing you might want to know. The input to the sigmoid function is called the logit. So essentially, the result of the forward method is, we can call that a logit. But this just makes the understanding a bit more complicated. So don't think about this too much. There's also one more thing that we need to go over before moving on with the code implementation, which is decision boundary. So the main difference, another difference between linear regression and logistic regression is how we use the model. In linear regression, we model the data itself. So in order to predict like a new data point, we could use the weights and biases and like multiply the weights with the data point and add the bias to it. We could get the prediction directly, right? This was regression, but because this is classification, we are not trying to map the data or the relationships in the data. We are trying to find a boundary that separates two classes from each other. This is important. Because this is classification, the line that we're going to find, the weights and biases we're going to get, are not going to represent like anything about the data. It's going to represent the decision boundary that separates our classes. Okay, you're going to understand this much better when we are going over the code implementation. So this is why classification can be done with calculating. Either these are probabilities. You don't really need to think much about them right now. And the sentiment to apply to an instance is decided using decision boundary. So we decide if a point is like a positive or a negative class. We use a decision boundary or a sentiment to do it. And which this case, you specify a number such as like 0.5. So you say that if the result of the sigmoid function is bigger than 0.5, then it belongs to class 1. Otherwise, it belongs to class 0. Okay. So that's it for the kind of general idea about logistic regression. We can talk about lots of other things too, but this is quite like, I just wanted to leave it as simple as possible. So let's just go over the code now. So the code actually hasn't changed when you from the linear regression example. We just changed how we generate the data and how we just use the model. It's quite similar to the linear regression example. So these are our imports. There's one thing that you need to note. We are going to use logistic regression class. I'm going to talk about that when we get to it. And there's also a clusters function, which we are going to use to generate the data points. Okay. Let's import everything, and these are our constants. This is going to be our device, which is going to be CUDA device. That is actually the dedicated GPU of my laptop. This is the data type. This is just an alias, almost like an alias. There's batch size, constant, number of epochs, size. This size signifies the how many data points are going to be in each of the classes. And the generator is used to like in random generation to kind of make sure that we are doing the same thing at each run. Let's print the device, and device is going to be my dedicated GPU. And so let's first run this code, and let's go over the clusters. Okay, the clusters method. So as I said it earlier, we have two classes. We have the positive class, which is 1, and the negative class, which is 0, right? We need to make sure that these can be separated. And the best way to do this is create like number of clusters with a certain amount of data points, and like just make sure that they are separated, and the clusters is the best approach. Okay, so because we are using a binary classification, we have two standard deviation and two mean values for both of the clusters, and that's it. So what we essentially do here is we use random distribution and generate two features for both of the for all the data points, and we multiply it with standard deviation and add the mean value to it. This will make sure that the cluster is located in the point we want, in a place we want. And then we generate its labels. Because it's negative class, it's going to be zeros. We're going to do the same thing with the positive class, but we're just going to change the zeros to ones because it's going to be positive class. And we're concatenating these two classes, so we just get two like the input data and the targets as one. Okay, and we return those. So it's quite simple. I just did this in a function, so it is much clearer and intuitive. So yeah, okay. So we generated our x and y, and let's actually see these. Look at these in a much more detail. So these are the data points. As you can see, these have two features in the form of columns, right? And let's look at the labels. So labels, as you can see, the half of them are zeros and the other half of them are ones. This is what we wanted. And the sizes are 200 by 2 because we wanted to have two features that kind of characterizes the data, and then we have just the same amount of targets for each data point. So let's plot the data to understand like how we generated the clusters. So as you can see, these are two clusters that we've generated. It is quite simple, like quite easy to understand when you see it in like visually. So these are both of the features. So as I stated earlier, we have two features. I decided on having two features because it's easier to plot, because we have x and y axis, right? So if I have just two features, I can just plot and just dedicate these two features into both into the axes we have, the x and y axes. So these are our clusters. The green cluster is the positive class and the blue cluster is a negative class. Okay, so again, let's move on. So next we're going to define our model. So let's go over the model definition. So again, I said that the linear regression and logistic regression are quite similar, right? Because of that, I didn't want to implement logistic regression from scratch. What I did is I inherited from linear regression, which I've implemented previously in the previous video, like this in this way. We use torch matmul. This is not the most practical way to implement it. I just, this is sort of my implementation. And we have the logistic regression, which inherits from linear regression. And this is initially the same, especially the initialization we have to do for both of the models are the same. So because of that, I defined the initialization method for the logistic regression and just made it the same with the initialization method of the linear regression model with using super method. This when we type the super here, we're just manipulating the parent class's methods and functions. Okay, so essentially this is just same as using this initialization method. So it's, I can just copy this from here and paste it here and it's going to be the same. I just wanted to do it this way. Okay, and there's another similarity between these two models. The forward method is essentially the same, with only difference being the usage of sigmoid function. So you can actually see that here too. We return a torch sigmoid function, and the input of it is the forward method of the linear regression. So I can also just write this return value here, torch matmul x, self w, and self b, right? But I didn't want it to do that because this is much more clear, and this kind of visualizes the similarity between the two classes. Okay, so that's how I implemented it. The sigmoid usage here is important, so that's how it is. So we define our model here, and input dimensions is 2 because we used two features. So let's create tensor dataset from both of the x and y, and we're going to get a tuple of tuple consisting of both of these elements. As you can see here, that's the only difference. And we are going to create dedicated data loaders for training data and validation data, which we are going to first split in with 80% of being training data and 20% of it being validation data. Okay, and we use the batch size constant here in the data loaders, and our initial batch size I think was 32, right? Let me check. Okay, we are going to use the batch size 32, which is going to just feed 32 data points at each iteration in each epoch. Okay, so I think it's going to be like how many updates? 32 divided by 3 or 4 updates, right? 3 updates, I think. Maybe 4 because there's some left out. Maybe I don't exactly know. Okay, so this is a trainer class. I talked about this previously in the linear regression video. This just encapsulates all the training process, so we don't have to like define all the training loop here. The only difference here is the criterion. We are going to use BCE loss, short for binary cross entropy loss, and we are again reducing to mean to get the average loss at each epoch. That's just what it does, and this is used for classification as well, even though it's just a classification loss. And all the other things are just the same. The optimizer is the same. It's still stochastic gradient descent, and yeah, device is device. This is just the CUDA device. I'm just stating that we're going to train it on the GPU. Okay. So next, we're going to train the model with .train method. This will also validate the method at each epoch too, and this also returns 2 dictionaries for each losses, train loss and validation loss. Let's train it. Okay, the training has ended. So let's look at the first epoch and the last epoch, and let's see if it improved, if the loss improved. So the first loss, the validation loss, is actually quite small, 0.03, right? So I'm sorry about that. So last loss for the last epoch is 0.02. So essentially this model hasn't improved too much, right? We're actually gonna see this in the plot when we plot the function. Yeah, this hasn't improved too much, and there is so much fluctuation between the validation loss, right? So this because I think this is because of the randomness. We are sometimes some of the points which are randomly selected might be closer to being outliers, so you will get a higher loss. Let's run this again. Okay, wait. Oh, I'm sorry. I need to do that first. Okay. Now it changed. Wait, why is this so bad? What? It shouldn't be that. That's interesting. Did I change something? I don't think so. What is happening? I don't understand. Let's run it all actually. Let's see what happens. Okay, so yeah, I think there's something about the generation. So this is much more easier to understand. So let's actually look at losses again. So let's see. So the first loss is 0.12 and the last loss is 0.006. So it definitely improved, right? So this is the loss. Normally the validation loss must be higher because this is not the data that you used to train it. So this is essentially a data that the model hasn't seen before. I don't know why it's lower here. I think that's just purely of chance. Let's print the model parameters here. So wait, so let me you know what, let's just leave it at that. So these are the weights and this is the bias. But as I said it earlier, this is not the model. This is these are the constants of our decision boundary. This is important. This is not like the model itself. Like this doesn't really map the values. So we are not going to multiply the weights with the input data and add the bias and we're going to get the result. No, this is just going to make sure that this is just the decision boundary that successfully separates the 2 clusters. That's why it's different. So now we are going to create the boundary, the line for the boundary. First, we created a tensor with lint space that maps all the values in X, the input data. So we cover all the data points. and we use size and data type and the device, and we reshape it to size 1. We use 1 here instead of 2 because we're just going to plot only one line. That's why we do that. You don't need to worry about that, because even though we reshaped this into 2, I don't think it's going to change too much. And we can actually do that. We can do this with copying this and concatenating with itself, but it's not going to change anything. It's going to be the same line, just you know just multiple times. So we construct the line with computing the slope and the intercept values for it. You can do this with like basic math. I'm not going to go over this. I think you need to do this by hand, like in a paper. Just write weights down and try to figure out how you can create a line function like a multiplied by x plus b, right? Y equals to a multiplied by a multiplied by x plus b. That's what it is. So this is the formula for it, as I stated. The slope multiplied by t x plus b. Right? This is the same thing. So we actually plotted it already. So this is, as you can see, the decision boundary that separates the two clusters, right? And we can clearly see that this separates it, but there is an error. One data point is misclassified. Why? Because these are too separated. This is most likely an outlier, because this is too close to the negative class. So maybe this is mislabeled, so that's why it's here. We can at least say that this is mislabeled, yada yada. It doesn't really matter. Let's run this multiple times and get different boundaries. There are some of them are much better, some of them are, as you can see, there are different types of boundaries. This is, again, this is perfect. This just separates two classes perfectly. There is no errors. There is no misclassified label or data point here. So that's how this code works. I hope that you understand it. I mean, I'm not the best at explaining things, especially these type of things. These are quite complex. Yeah, that's how it works. This is the code, and you can also run this code. I also have a run file for this. You can also directly run it as a script, I think. Let's try it actually. So do I need to go? No, I can just type in Py, right? So this is just gonna run it as a script. Yep. And you're gonna get the results of it. You can also do this too. This is fine. You can also just run the code directly without really working with the Jupyter Notebook if you don't like to. This also works. Okay, so yeah, that's it for the video. I hope that you enjoyed it. Yeah, that's it, and thank you for listening, and see you soon. Take care, guys, and goodbye.